Good afternoon, everybody. I hope everybody had a great lunch. My name is Dietmar Stoll from the company Itemis Switzerland. This is Lorenzo Bettini from the University of Turin. This is a joint work with my CEO, Serrano Colameo of Itemis Switzerland and Markus Wölter of Itemis Germany. Today we're talking about a topic which has become increasingly important for domain-specific languages, DSLs, and will continue to gain attention in the community. What are type systems? Are they useful? There are a lot of DSL tools out there. For example, MPS, Spoofax, Rascal, Essential, Xtext, and many more. And quite a number of these DSL tools have become mature, comprehensive, and user-friendly. In other words, it's really easy to build your own language these days. It's even easy to build a complex language. And complex languages usually require complex consistency checking. All these languages usually have data structures, assignments, expressions like mathematical operators or function calls, and these are all related to types. So, why don't we exploit the commonalities between these languages with type systems to save ourselves time and effort? After an introduction, I will present a case study language which allows to edit GUI forms for editing entities. And we will use Xtext as the DSL development environment, and we'll use plain Xtext, Xbase, and two type systems called Xsemantics and XDS. Imagine a language where I can define variables using expressions on the right-hand side. For example, greeting uses a concatenation of a string literal and a name variable. Here, the system has to know that hello is a string literal of type string, name is a variable of type string, and that the concatenation of two strings yields a string. And in this small example, you've seen almost everything that a type system does, which is assigning types to language elements, inferring the types of complex expressions like the plus operator, and answering questions like, is it okay to supply a float when I expect an int, or the other way around? In our case study, we have a language that allows to specify GUI elements for form-based editing of entities for the end user. The entities can have primitive attributes and derived attributes, and the forms have widgets like text box widgets, checkbox widgets, and validation clauses, for example, to specify the input range of input values or the length of textual inputs. So this is our case study. Now this is, no need to read all details, this is how the textual language looks like in the DSL editor. In the upper half of the screen, I defined an entity person with various attributes of various types. In the lower half, I've defined a form which edits this entity I've just defined. And this form includes, for example, an attribute, a text box widget, which edits the name entity, the name attribute of the entity. And it has a validation clauses which restricts the length of the input to be at least 1 character long. Of course, a good IDE should complain if there's something wrong or if there's something which makes no sense. For example, if the developer assigns a checkbox widget to a non-Boolean attribute, for example, assigning a checkbox to an attribute of type string. How can the IDE complain? Only if it knows about types. And this is how we implemented the type knowledge. In the plain Xtext approach, we have used an implementation using Java and Xtend to keep the code concise. It basically consists of two classes. One class is recursively computing the actual and expected type of language elements, and the other class answering questions whether one type is assignable to another type. And these two classes are called from the standard Xtext validator. So the type provider has to answer what actual type is my language model element. For example, if I have a language model element which is an int literal, it's just an integer type. If I have in my language a plus operator, the actual type of the plus operator is the most general type of its operands, but which also could be object. But the expected type of a plus operator in our language is either a string or something more specific. And the methods, most general and most specific, relate to type assignability. And this is the responsibility of the next class. It consists of a bunch of isAssignable methods, and it uses polymorphic dispatch to keep the code base small. And it answers questions like, if I expect type A, am I allowed to supply type B? For example, if I expect a string type, am I allowed to supply a number type? In our language, that is the case. So now you have already seen the idea of the basic approach using just plain Xtext and Xtend. Now, using Xbase is something special because Xbase reuses the Java type system. So, in Xbase, we slightly modify our grammar so that the entity attributes directly refer to Java types and the derive expressions directly refer to expressions of the Xbase library. And entities themselves and forms are converted into Java classes with the JVM model inferrer. I don't want to go into detail, I just want to show you the size of the implementation. For example, this method, a method of this size, yields an automatically generated Java class complete with attributes, getters and setters. And that's it for the Xbase approach. Everything else is taken care of by the Java type system.
Now I'm going to present two frameworks for writing type systems for Xtext languages. I'm just giving a very brief overview of these frameworks. These are two open source frameworks, so you can find much documentation online. I'm starting with Xsemantics. Xsemantics is not actually only a framework only for type systems. You can define any kind of rules for the elements of your language implemented in Xtext. So you can define type systems, but also reduction rules or interpreters or any kind of relation rules. And it is a language thought to be used by people who are familiar with formal systems, so people who work on formally defining and designing a language. And the system definition is a set of judgments. You define the judgments of your system. For instance, this is a judgment type which uses this symbol and then has a parameter, an input parameter and an output parameter. And here you can choose among some predefined symbols, and these are the symbols which are usually used when designing formal type systems or operational semantics. And then you can define the rules of these judgments. And of course, starting from this system definition, you will have generated Java code for this system and also a generator, a validator for your language. So as I was saying before, this DSL is thought to be used by people who are doing theory on languages. So for instance, if you had to write formally the type system for our language, I would write rules of this shape. So I would say that the literal true has type Boolean, and this is an axiom. It has no premises. Then I could say that a reference to an attribute has type T, provided that the referred attribute has type T. So these are natural deduction rules which can be axioms or which can have a conclusion and a set of premises. Xsemantics DSL is pretty close to this syntax. It's just that the rules are written in the other direction. So I write the conclusion first and then the premises. Xsemantics reuses Xbase for the syntax of the premises. So you have a pretty expressive language for defining the premises of your type system. And these are the rules which correspond to the rules that I would write if I had to define formally the type system of my language. And of course, in the premises, you can either invoke other rules or write any Xbase expression. And this is just another example. Let me skip quickly through this. Then you can write specific rules which are used to generate the validator for your language. For instance, this check rule says that a widget is correct if either the validate feature is null, because if it's null, there's nothing to check, or if I can derive a Boolean type for the validate attribute using a specific typing environment. So I can pass to the rules other mappings for the elements of my language. And as I was saying before, in the premises of the rule, you can either invoke other rules or write any Xbase expression. Starting from the system definition, you will have a generated Java system, but you will also have a generated validator for your language. That validator reuses the rules you had written for your system and automatically generates error markers. Usually the strategy for generating the error markers is okay, but if you're not happy with that, you still can customize anything. So you can, if you want to generate a different error marker, you can still do it. Also because when the rules are applied, automatically the trace of the applied rule is stored. So you always have access to the trace of the applied rules. This can be useful for generating error markers, but also for testing and for debugging. This is a feature which also the XTS framework I'm presenting in a minute has. So we are using Xsemantics because we are doing theory on languages, and when you design a language from a formal point of view, you usually write the type system rules, then you write the operational semantics, which says how the expression reduce, and then you have to prove formally that the operational semantics is consistent with the type systems. This will guarantee that if a program is well typed, at runtime it will not get stuck due to a type error. But once you've done the theory, you would like to also to have a quick prototype implementation. We are using Xtext for have a quick prototype implementation of our language, and we also use Xsemantics because it allows to quickly translate in an actual program the type system rules and the operational semantics rules that we saw, that we wrote in our formal system. Xsemantics is not a proof assistant, but it can help you in proving that the semantics is consistent with the type system. XTS is another type system framework for Xtext. It's written by Markus Wolter. It's a Java framework that allows you to specify in a declarative way the type system rules, but it also has a DSL to write the type rules in a more compact form and to have Java code automatically generated. In XTS, you have to refer to the eCore of the eCore file which contains the metaclasses that Xtext generates for your language. So once you access the eCore, you can access the eClasses of your AST and the features of the AST. And I'm not getting into the details, but you can define type system rules in a very compact form with respect to X semantics, because XTS only focuses on type systems. And if the expressivity of XTS is not enough, you can still say that for typing this specific element, I will write later Java code. Of course, you can do also recursive computation. You can define characteristics of your types, and you can use these characteristics to write the other type system rules. For instance, here you say that a comparison expression has type bool, provided that both the left and the right sub-expression have a type which belongs to the characteristic comparable. And similarly for the minus expression, you require that both sub-expressions have a type numeric. Similarly, you can write more complex rules, and also in this case, you will have Java code automatically generated.
Here are some criteria which might help you in deciding which approach is best for you. We are right now writing an article and will publish it and elaborate on criteria such as context, expressivity, verbosity, customizability, additional features, your target audience, documentation, support, and more criteria. Just to pick two criteria, for example, if you are reusing the Java type system, then Xbase might be your best bet. If you are using another type system, you might as well choose one of the other three approaches. The expressivity of the approaches also varies. For example, the plain approach uses Java and Xtend, and Xbase has the expressivity of the Xbase library, and the individual type systems like XTS and Xsemantics have their specific syntax. In summary, type systems solve common tasks like type inference and type conformance computing. There are many type system framework applications. For example, we had a project with a DSL to model the cooling behavior of refrigerators. We are right now on a project to map to and from a type system of the financial domain called ISO 222. We recently had a project with a service description language which generated Java artifacts and which reuses WSDL, Corba IDL, and Java types. And we have implemented formally described languages with type systems, and we also had a project with a C-like language for hearing aid configurations. With type systems, you can also do more advanced tasks like writing interpreters or dynamic type computation. So, my conclusion is type systems are very useful. They are used in lots of real-world projects. So, it may be well worth considering type systems when you write your next DSL project. Thank you.